In the last video, I spoke somewhat theoretically about what a null space is, and we showed that it is a valid subspace. But in this video, let's actually calculate the null space for a matrix. And in this case, we'll calculate the null space of matrix A. So the null space is literally just a set of all the vectors that when I multiply A times any of those vectors. So let me say that the vector x1, x2, x3, x4 is a member of our null space, that when I multiply this matrix times this vector, I should get the 0 vector. I should get the vector. And just to make a few points here, this has exactly 4 columns. This is a 3 by 4 matrix. So I've only legitimately defined multiplication of this times a 4-component vector, or a member of Rn. Let me call this x. If this is our vector x, this is a member of R4. It has 4 components. And then when you multiply these, we need to produce the 0 vector. The null space is the set of all the vectors. And when I multiply it times A, I produce the 0 vector. And what am I going to get? I'm going to have one row times this. And that's going to be the first entry. Then this row times that's the second entry. Then the third row. So I should have 3 zeros. So my 0 vector is going to be kind of the 0 vector in R3. So how do we figure out the set of all of these x's that satisfy this? Let me just write kind of our formal notation. The null space of A is the set of all vectors that are a member of, you generally say Rn, but this is a 3 by 4 matrix. So these are all the vectors that are going to be members of R4, because I'm using this particular A, such that my matrix A times any of these vectors is equal to the 0 vector. In this case, it's going to be the 0 vector in R3. So how do we do this? Well, this is just a straight up linear equation. We can write it that way. If we were to actually perform the matrix multiplication, we get 1 times x1. Let me write it here. Let me do it in a different color. 1 times x1 plus 1 times x2 plus 1 times x3 plus 1 times x4 is equal to this 0 there. It's equal to that 0. So that times that is equal to that 0. And then this times this should be equal to that 0. So 1 times x1. So you get x1 plus 2 times x2, 2 times x2, plus 3 times x3, plus 4 times x4 is going to be equal to that 0. And then finally, we have that times this vector should be equal to that 0. So, you can have the dot product of that. The dot product of this row vector with this column vector should be equal to that 0. So you get 4x1 plus 3x2 plus 2x1 plus x4. Oh, sorry, what am I doing? Plus 2x3. Right, plus 2x3 plus x4 is equal to 0. 4x1 plus 3x2 plus 2x3 plus x4 is equal to 0. And we just have to find the solution set to this, and we'll essentially have figured out our null space. Now, we've figured out the solution set to a system of equations like this. We have 3 equations with 4 unknowns. And we can do that. We can represent this by an augmented matrix and then put that in reduced row echelon form. So let's do that. So I can represent this problem as the augmented matrix 1, 1, 4, 1, 1, 4, 1, 1, 4, 1, 2, 3, 1, 2, 3, 1, 3, 2, 1, 3, 2, and then 1, 4, 1. 1, 4, 1, and then I augment that with the 0 vector. And the immediate thing you should notice is, look, we took the pain of multiplying this times this to equal that, and we wrote this as a system of equations. But then now that we want to solve the system of equations, we're kind of going back to the augmented matrix world. And what does this augmented matrix look like? Well, this is just our matrix A right there. That's just matrix A right there, and that's just the 0 vector right there. And to solve this, and we've done this before, we're just going to put this augmented matrix into row echelon form. And what you're going to find is when you put it in a row echelon form, this right side's not going to change at all, because no matter what you multiply or subtract by, you're just doing it all times 0. So you just keep ending up with zeros. So as we put this into reduced row echelon form, we're actually just putting matrix A into reduced echelon form. So let me do that instead of just talking about it. So let me start off by keeping row 1 the same. Row 1 is 1, 1, 1, 1, 0. And then I want to eliminate this one right here. So let me just subtract. Let me replace row 2 with row 2 minus row 1. So 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. 0 minus 0 is 0. You can see the zeros aren't going to change. And then let me replace this guy with 4 times this guy minus this guy. So I get, because I want to get rid of this. So 4 times 1 minus 4 is 0. 4 times 1 minus 3 is 1. 4 times 1 minus 2 is 2. 4 times 1 minus 1 is 3. 4 times 0 minus 0 is 0. Now I want to get rid of, if I want to put this in reduced row echelon form, I want to get rid of that term and that term. So let me keep my middle row the same. My middle row is 0, 1, 2, 3. Keep middle row the same. So that's 0 on the augmented side of it, although these zeros are never going to change. So it's really just a little bit of an exercise just to keep writing them. And then my first row, let me replace it with the first row minus the second row so I can get rid of this 1. So 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 2 is minus 1. 1 minus 3 is minus 2. And 0 minus 0 is 0. And let me replace this last row with the last row minus the middle row. So 0 minus 0 is 0. 1 minus 1 is 0. 2 minus 2 is 0. I think you see where this is going. 3 minus 3 is 0. And obviously 0 minus 0 is 0. So this system of equations has been reduced to just by doing reduced row echelon form this problem. If I just rewrite this right here, this can be written as a system of equations of x1 minus x3 minus x4, right? The 0 x2s is equal to 0. And then this second row right here could be written as there's no x1, so you just have an x2 plus 2x3 plus 3x2 is equal to 0. And this obviously gives me no information whatsoever. And so I can solve this. I can solve this for x1 and x2. And what do I get? I get x1 is equal to x3 plus x4. Actually, I made a mistake here. This is x1 minus x3 minus 2 times x4 is equal to 0. So if I rewrite this, I get x1 is equal to x3 plus 2x4. And then I get x2, let me do that in green. x2 is equal to minus 2x3 minus 3x2. And so if I wanted to write the solution set to this equation, if I wanted to write in terms of this, I could write x1, x2, x3, x4 is equal to, what's x1 equal to? It's equal to x3 times 1 plus x4 times 2. Right? I just got this right here from this equation right here. x1 is equal to 1 times x3 plus 2 times x4. That's just that right there. Now x2 is equal to x3 times minus 2. That's x3 times minus 2 plus x4 times minus 3. What am I doing? I'm losing track of things. This x2 right here is x2 plus 2x3 plus 3x4 is equal to 0. So x2 is equal to minus 2x3 minus 3x4, right? Like that. Sorry, my brain isn't completely in the problem. I'm making these silly mistakes. But I think you understand this now. And then what is x3 equal to? Well, it's just equal to 1 times x3. It's equal to 1 times x3 plus 0 times x4, right? x3 is equal to x3. And what's x4 equal to? It's equal to 0 times x3 plus 1 times x4. So all of the vectors in R4, these are a member of R4, which satisfy the equation, our original equation, ax is equal to 0, can be represented as a linear combination of these two vectors, right? These are just random scalars that are a member of, we can pick any real number for x3, and we could pick any real number for x4. So our solution set is just a linear combination of those two vectors. Well, what's another way of saying a linear combination of two vectors? So let me write this. The null space of A, which is just a solution set of this equation, it's just all of the x's that satisfy this equation, it equals all of the linear combinations of this vector and that vector. Well, what do we call all the linear combinations of two vectors? It's the span of those two vectors. So it equals the span of that vector and that vector, of the vector 1, minus 2, 1, 0, and the vector 2, minus 3, 0, 1. And this is our null space. And before letting you go, let me just point out one interesting thing right here. We represented our system of equation like this, and we put it into reduced row echelon form. So this is A, and this is 0. This right here is, let me make sure I have some space. Let me put it right here. That right there is the reduced row echelon form of A. And so we're essentially, this equation, this is a linear equation that's trying to solve this problem. The reduced row echelon form of A times our vector x is equal to 0. So this, all the solutions to this are also the solutions to our original problem, to our original ax is equal to 0. So this, what's the solution to this? All the x's that satisfy this, these are the null space of the reduced row echelon form of A. Right? So this is, so here all of the x's, this is the null space. This problem, if we find all the solution set, all of the x's here, this is the null space of the reduced row echelon form of our matrix A. But we're saying that this problem is the same problem as this one, right? So we can write that the null space of A is equal to the null space of the reduced row echelon form of A. And that might seem a little bit confusing. Hey, why are you even writing this out? But it's actually very useful when you're actually trying to calculate null spaces. Because we didn't even have to write a big augmented matrix here. We could just say, OK, take our matrix A, put it in reduced row echelon form, and then figure out its null space. So we would have gone straight to this point right here. This is the reduced row echelon form of A. And then I could have immediately solved these equations, right? I would have just taken the dot product of the reduced row echelon form, or not the dot product, the matrix vector product of the reduced row echelon form of A with this vector, and I would have gotten these equations. And then these equations would have immediately, I can just kind of rewrite them in this form, and I would have gotten our result. But anyway, hopefully you found that reasonably